Hello, and welcome to Unit 16, Net Ionics and Titrations. So this unit has basically just two components to it. The first are these complete and net ionic equations that we're going to cover. The second one, will be a second video, we'll cover titrations. We'll get to that later in the week. So starting off with electrolytes. And more importantly, what classifies or constitutes a strong versus a weak electrolyte. So electrolytes are compounds that when they dissolve in water, they're going to break apart and form positive and negative ions, which you can then conduct electricity through that solution because of those positively and negatively charged ions. So some compounds will dissolve fully. We call those soluble, and we've already kind of worked with them a little bit. We have the solubility table on the back of our periodic table, and it has the AQ telling us that they will dissolve, they will break apart in water. If they're strong electrolytes, that means that they're going to break apart every single time. So we see sodium chloride here. Every single sodium chloride that we put into water has dissolved, has broken apart, so we're left entirely with sodium ions and chloride ions. Weak electrolytes, the middle image here with hydrogen fluoride, weak electrolytes don't always dissolve. So sometimes they might, oftentimes they won't. So here's the picture of HF. See, a lot of those HFs are still together. They haven't dissolved. They're still in their compound form. Just a couple of them will dissolve. And then there are other examples of non-electrolytes. Sugar, for example, is a covalent molecule. It's not going to dissolve into positive and negative ions, so it's a non-electrolyte altogether. In this chapter, we're really going to take a look at acids as well, strong versus weak acids. So strong acids, just like with strong electrolytes, are going to dissolve completely. So here's a picture. We have a bunch of positive charges that have dissolved. If you guys remember back to our naming unit a couple months ago, acids always have to start with an H. So here are the H pluses. They have completely dissolved, and it left us with an anion. That would be the negatively charged part of the acid. So there's a strong acid, completely dissolved, and here's a weak acid. Notice again how several of the H plus and negatives are still together. They haven't completely dissolved. Some have, like this guy here, he's broken apart, but many of them are still together. And that's what we call a weak acid. There are 5 strong acids that you guys are responsible for knowing, so make sure you memorize these 5. So whenever you see one of any of those 5, you know that it is a strong acid, and that H is going to come off every single time. So if I tell you have 100 HCl's, that really means you have 100 H pluses. Weak acids, again, they don't ionize completely. So here are some weak acids. You've got your list of 5 strong acids to memorize. All other acids are considered weak acids. All right, so that brings us back to complete and net ionic equations. So we worked with these types of reactions already. We just didn't delve into the complete and net ionic part when we did so. So way back in January when we did our reactions unit, you would have taken a look at double replacement reactions. And that's where we start with our complete and net ionic equations. So when ions dissolve in water, we call them, again, we call it aqueous, AQ. We put that state of matter after it. And then we usually have, for a complete net ionic equation, what we call the driving force. And the driving force is going to be the formation of something that is not aqueous. Could be a solid, gas, or liquid. You're oftentimes going to have the liquid water, and that often happens when you dissolve an acid with a base, and you get what's called a neutralization reaction. An acid and a base will neutralize each other, and water is one of the products. So we write our full equation. We start off writing our full equation. We identify the states of matter, and then we write what's called the complete ionic equation, where we show all of the ions. Again, when a compound is aqueous, AQ, that means that it's dissolved in water, and it's really not a compound. It's broken apart, and you have your ions. So the complete ionic, the CIE, will show us all of the ions in the equation. The next step is to eliminate the ions that aren't really doing anything. If they start off as being an ion on the reactant side, and they end as an ion on the product side, then they really didn't take part in the reaction at all. They're called spectator ions, because really they're just there watching like a spectator. So we eliminate those, we get rid of them, we don't have them in our final equation. Our final equation ends up being what's called our net ionic equation, NIE. So net, because it's showing us only what's there. So make sure you guys have your periodic tables, and the back side especially, ready to go. Well, let's take a look at an example. So iron 3 chloride and potassium hydroxide. All right, so the first step is to write the full equation, predict the products. Again, I know it's been a couple of months, but hopefully this comes back to you pretty quickly. The positively charged iron, is going to match up with the other negatively charged ion. So currently it's with the negative chloride. Now it's going to match up with the negatively charged hydroxide ion. So that'll be iron hydroxide. And then potassium, the K, is going to switch and form with chlorine. We have to make sure we balance it. And so there is our full equation. Again, this is what we've already done a couple of months ago. Might take a little bit of review and a little bit of practice, but that's all right. I know we're capable. The next step is the CIE, the complete ionic equation. So in this step, we're going to break apart all of our aqueous compounds. So FeCl3 here, aqueous. What aqueous means is that it's really not one compound, FeCl3, but really we have an iron plus 3 ion. Make sure you put that that's aqueous. And 3 chloride ions. Again, make sure you list that those are aqueous. Ions really only exist inside of water, so it has to be aqueous. Potassium hydroxide is the same thing. It's really not one big gigantic KOH. It's really broken into a K plus 1 and 3 OH negative ones. Sorry, there should be 3 in front of the K as well from the 3 here. And again, all of those are aqueous. So there's our reactants. On the product side, this is important, the FeOH3, the iron 3 hydroxide, is solid, not aqueous. So it is not dissolved. That would be our precipitate. It is not broken apart. So make sure you do not break your solids apart. Only your aqueous states of matter get broken into their ions. So the solid stays together. KCl, potassium chloride, is aqueous, so we will go ahead and break those ions apart. The final step then is to rewrite the equation and eliminate the ions that didn't change. They weren't a part of the reaction. So we look up here, we say, okay, Fe3 plus and Fe. That's a change. He reacted, so we're not going to eliminate iron. So we'll keep him. Plus, let's take a look at our next substance here. Chloride ion. Chloride ion. Notice how we have 3 Cl negative ones on the left and 3 Cl negative ones on the right. Well, he's a spectator ion. He didn't do anything. So I'm not going to keep him in my net ionic. The potassium ions then, they're next. Potassium ions, again, they didn't change. Nothing happened. So they're what's known as a spectator ion. We will not put them in our net ionic. Next up, we get to hydroxide. We have 3 OH negative ones on the left. And on the right, it's iron hydroxide. So the hydroxide ions were a part of the equation. So we'll go ahead and add those guys. They did change. Make sure you keep that 3 there with them. And so iron plus 3 and 3 hydroxide ions are going to react to form solid iron hydroxide. And this is our net ionic equation. So yes, we did have this big gigantic equation up top, but in reality, the only thing that's happening here are iron ions are reacting with hydroxide ions to form iron 3 hydroxide. And this is our net ionic equation. The final thing to do then is to identify your driving force. In this case, it's the formation of a solid. So we mentioned it a minute ago, a very special type of double displacement reaction is called a neutralization reaction. And this is when an acid reacts with a base. You're always going to form water and an ionic compound called a salt. So for example, we have acetic acid. There's the ion acetate with this H plus in front. That makes it an acid. And we have sodium hydroxide. Sodium hydroxide here. That's our base. So again, we're going to write our full equation first. The positively charged sodium ion is going to partner up with the negatively charged acetate ion, form sodium acetate, and water, HOH. So to write the complete ionic equation here, there's our acetic acid, our sodium ion, and our hydroxide ion. Those guys are aqueous, so we split them apart. You might be wondering why we didn't split apart acetate. Well, he's not a strong acid. Remember that list of 5 strong acids I recommended you to memorize? Well, acetic acid's not on there. So he's not a strong acid, so he's not going to dissolve completely. So we'll leave him together, even though we have identified his state of matter as aqueous. Only the strong acids dissociate. So again, make sure you have those 5 memorized and recognize them when you need to. So on the other side, sodium acetate is aqueous, so we'll split up sodium. And the acetate ion. And water is a liquid, so we don't break him up. Again, if it's not aqueous, don't break him up. If it's not a strong acid, don't break him up. Okay, the net ionic part now. We want to eliminate our spectator ions. Okay, well, acetic acid started off as HC2H3O2. I don't see that anywhere on the right, so that must mean he's a part of the reaction. We'll keep him. Sodium ion and sodium ion. Sodium did not react here. So we will eliminate him as a spectator ion. That brings us to the hydroxide ion. The hydroxide ion is OH-1 over on this side, but it's water over here. So he did change, so we'll eliminate him. Brings us to the product side now. Again, we've already gotten rid of the sodium ion as a spectator, so he's no longer there. But acetate, we are going to eliminate him. I'm sorry, we are going to keep him in the equation. He did change. And so here's acetate reacting with hydroxide ion to form acetate ion and water. And the driving force is the formation of our liquid water. So again, the driving force is always going to be the formation of your non-aqueous product. Just a quick note, you might see this from time to time. If you go through the full equation and every state of matter you correctly identify as aqueous, then that means there is no reaction. So when you get down to the net ionic equation part, you just put an NR. So I would still expect to see the full equation. I would expect to see the complete ionic equation, except everything would be broken apart. Everything would be dissolved. You'd have nothing but ions. Everybody would be a spectator ions. You'd get down to the net ionic equation and you'd write in R, just like we did for our single displacements when they didn't react. All right, you have some homework tonight. You've got 4 net ionic equations to write. You need to show all parts of it. So the full equation, identify the states of matter. You're going to use your solubility rules on the back of the periodic table. The complete reaction, so that's where you show all the ions. And then finally, the net ionic equation, where you eliminate your spectator ions and write only what happened.